Luis.
Hi. Can you hear me?
Yes.
Okay, great. Brendan, great talk. And I apologize if this question is a little bit more general than I think maybe I should be allowed to ask. But one thing that I wanted you to see if you could follow up and discuss a little bit is within the framework that you've been discussing, which is quite general, a couple of aspects that are emphasized explicitly and implicitly are the issues of spatial localization as well as causation, in the sense that the models that are discussed or considered to some extent are fairly spatially localized in terms of the mapping of structure and function. And the notion of causation that you entertained seems to be sort of like a sort of traditional causation that is very common in science, but it leaves open the question of how do we broaden it so that we understand the mapping between structure and function in the brain from a more complex systems type of view. So what I wanted you to see if you could comment is, how do you view these issues of spatial localization and causation, and what role can we bring into CCN or other types of venues and projects of a more complex systems approach in which complex computations are spatially and temporally distributed, and in which causation is something that is misguided is way too strong a word, but traditional causation, if you will, is a little bit misguided in the sense that it's not something that we can define the top and the down, top-down mechanisms, the bottom-up, or it's much more intertwined than we usually convey with boxes and arrows and the like. And again, I apologize for such a lengthy question and open-ended topic.
It's all right. Brendan?
Can you hear me okay? Okay. Thank you for the question, Luis. So when I was writing this sort of rapidly writing this paper for this, I had thought a little bit about this. I mean, there is in the philosophy of science, in philosophy of neuroscience, kind of ongoing discussion, for instance, about how to relate mechanistic approaches to things like connectivity or dynamic systems. And the short answer, the sort of short, boring answer to the question, and disappointing answer, is that I'm not sure what I think about these things yet. I think you're totally right that there is a particular focus of the way that I've characterized things, and that in terms of plausibility and explanation, and that was kind of self-consciously done because I wanted to kind of try and get clear, at least to myself, what I thought about this sort of case. As you say, the sort of traditional causal process, the sort of very traditional way of thinking about spatial localization. And in some sense, I was kind of focused on why I took these simple cases, and then the idea is wondering how things branch out from there. This sort of thing that I would say, though, is that I don't, although I tried to, I characterize the notion of plausibility within a certain way of thinking about what you're trying to explain. So if one thinks that when one uses a sort of more distributed or complex systems approach, insofar as the phenomenon that you're trying to explain might be different than what sometimes the focus of mechanistic explanation, then it might be that we should be characterizing a notion of model plausibility and explanatory plausibility that's relative to those explanatory variables. So it might be that, depending on what you think the relationship is between mechanistic explanation and complex systems approaches and forms of explanation that use those methods, then so a lot of what I say might not actually apply to that case very well. But this is like that's something that I'm kind of not sure what I think about yet. This is basically kind of a bit of a flaccid answer to your question, unfortunately.
Well, thanks. Anyway. Okay, so thanks, Luis, for your question. I have just muted you, but if you want to add something later, that will be possible. Now, if there is no further clarificatory question from the attendees, there is one. And so let us speak John. John, welcome back.
Thank you. Can you hear me?
Yeah.
Yeah, hi, Brendan. It's John Krakow here. Just following up on that last question, it seems to me from your talk that the Craver mechanistic framework, which is very much dependent on physical configuration, in other words, impingement of an object on another object, is doomed. And in all the examples you gave, what ended up happening is that your neural data was confirmatory, but it never gave you any indication in a Craver-esque way of how the physical configuration, for example, the diffusion to bound model, nothing about how the actual configuration of that IP does it. So in other words, your implementational plausibility, your biological plausibility is just to have a correlate of your algorithmic model. And your psychological plausibility is just to be able to make sure it correlates with behavior. And the Craver framework has nothing to say. And that's because, you know, as you correctly said at the end, the dynamical systems, complex systems viewpoint as physicists have known for a long time is that the science of the patterns of interaction and the science of the objects that are interacting are different sciences. And if cognition is going to map onto patterns of interaction, that's a different framework to the actual science of the objects in their physical existence. So it seems to me, unless I've misread your talk, that the Craver physicality requirement just doesn't work.
Well, so I think it's important to get clear is that, I mean, I made the distinction between composition and localization. And while in sort of simple intuitive cases like the cash register, there might be like a very clear mapping of, or this comparatively clear mapping of function to structure. That's not an intrinsic presumption of the mechanistic approach. So there can be a kind of many-to-one or very complex relationship between from function to structure. Now, I think that what you said earlier in terms of how the approach connects to mention the drift diffusion models and stuff. I mean, I think that those sorts of models, as you say, I mean, you're right that whatever extent something like a drift diffusion model, as it's normally used, maps onto anything about the way the brain is doing things. I mean, that's at best very, very indirect. And so I didn't want to suggest that there's going to be some sort of simple mapping. That's why they're described as being kind of mechanism sketches. So they provide only very abstract or incomplete and very high level. I mean, though, you know, if I do a boxology of like an evidence accumulation model, I mean, those boxes don't, it's not like I have the evidence accumulation box in my head or something like that. I mean, you're obviously subsuming whatever the actual functional decomposition is going to be something much, much more complex and much, much more distributed. I take that as in some respects to be sort of a weakness. I mean, it means that we would have to have much, much better models if we wanted to actually relate behavior, if we want to actually relate them to neural structure. And my focus on them is just because they're familiar models and because they're the models that people are actually using. I think that the way that the mechanistic approach comes in is that it's actually pointing towards a kind of normative ideal for explanation. But I think that these sorts of models, even from a psychological perspective, are like very, very distant from what that ideal sort of is supposed to demand of us. I don't think I answered all aspects of your question.
Can I answer back? Am I allowed to answer back a minute, Marco?
Sorry, you want to follow up?
Yeah, just for a second. I guess what I'm
Very
saying
quick
is,
one, it's
yeah,
okay.
all I'm asking is that the goal, it seems to me, in the Craver mechanistic view, is that you have something to say about how structure, physical structure, maps onto computations and representations. And all I'm saying is I could see nothing in your talk where a credible mapping between physical structure onto computations and representations happened. All one got was correlations with code. That's just a correlation. It doesn't tell you anything.
Yeah. Oh,
it never happened, not once.
Oh, yeah, that's right. I wasn't. That's definitely right. But I was not trying to offer an account of what that mapping would be like. But I mean, I agree. You're right in terms of what the actual sorts of studies I showed. You're totally right that these are sort of correlational studies. And I mean, under Craver framework, mechanistic framework, there's usually an emphasis on things like manipulability and intervention if one wants to be able to make stronger causal claims. And I definitely did not touch on anything about that in this talk.
Thank you.
Okay, thanks, John. I think that it is time for the discussants' questions. So I invite Lena and Nikolaus to activate their camera, if they will, and their microphone. So please, Lena.
Yeah, thanks, Brandon. Lots of stuff in that talk. I agree. I have two quick clarificationary questions, if I may, and then I have like a big picture question, depending on which also ledges on a bit to what you already discussed with John. So, but let's take the small ones first because they might actually fuel some of the stuff in the big question.
Yeah.
So, first of all, do you take mechanistic explanations to be models? Is that right?
So I said that mechanistic explanations are description. I said they're descriptions of mechanisms, and then I think I was probably a bit loose in the way that I was talking, but I talked following Craver and Kaplan about whether or not the model has explanatory force, which is, I take it, dependent on some sort of interpretation that one has of a model. So I take it that a model is just a formalism. A model by itself doesn't explain anything. We have sort of interpretations of models and applications, applied in certain situations.
The reason that I'm asking is because you have these different distinctions between different kinds of explanations and or models, and they seem to be running together at some points, and they seem to be coming apart at other points. And I'm just wondering how or to what extent or whether at all you distinguish between explanations and models.
Yeah, so I was, so the short answer is yes, I think that we have to distinguish between models and explanations. I mean, one way in which we try and explain things is by making models of them. Of course, just to be clear, by the way, I'm thinking about models. And this might be part of the problem. I was thinking of models like as formal models, right? So of course, there's many different ways as formal models, like mathematical models, right? So of course, if you have, if you have a more, and I should have been much clearer about that earlier. If you have a more general definition of model, then it might be that. So if you have a very general sense of model, it could be that any description of a mechanism is a model. But I was thinking more in terms of mathematical models.
Okay, sure. Okay, that's helpful. So that then almost leads to the second clarificationary question, because I'm not quite so sure what the measurement role of a model precisely is and how that is different from the explanatory role.
Yeah, I was
flesh out a little bit.
Yeah, that's something which I'm I think slightly clear on in the paper, and I think I was very much kind of at the short end of the stick in the talk. So I think that a model is being used in, I mean, one way of drawing the distinction, one aspect of the distinction is that a model is being used in an explanatory role when it's satisfying something like it satisfies like the M3M star condition, and it's being used in a context in which we're trying to like evaluate the explanatory force of the model. So if we're saying like, oh, we might say the model explains some stuff and we want to see how it explains other stuff as well, and say in comparison to some other model. So if we're actually evaluating the explanatory force of the model, it's being used in an explanatory role. When it's used in a measurement role, we're not trying to reevaluate or evaluate the explanatory force, but we're just using it in a way where we assume whatever explanatory force it has is fixed, but we think that the model allows us to provide evidence of some sort of phenomenon that we're interested in. So, so this is a part where I get a bit clear myself, because I make this talk about how a mechanistic model can be used to explain a phenomenon or provide evidence of a phenomenon from data. And I think that when it's used in a measurement role, it's being used in that second way. So going from data to provide evidence of a phenomenon.
So could you say that when I use a model that's already there to express or represent a bunch of data, then I'm using it as a measurement tool? Would that be the idea?
Yes, that's basically the idea. And
when I'm using it to explain, I'm telling you how this data pattern came about. Story.
Well, I mean, I think this is where it gets a little tricky, because I mean, in a sense, you know, it's when it's used in a measurement role, right? It's still presuming that it has some sort of explanatory force. So the evidence accumulation model, we assume that there's some evidence accumulation process, and that's why the data has the distribution properties that it has. So there's, you know, there's one, so it still has that sort of, to the extent it has explanatory force, it still has that for accounting for why the data has the property, the phenomenon of what the distribution is like. But the idea is that there's this other thing that we might care about, which is that, oh, why is it that we take longer to respond in one condition versus another? We might say, oh, that's because the drift rate parameter is different between these two conditions. But what we're actually trying to explain then is what accounts for why there's this difference. You know, what about the stimulus or something else is accounting for why we take longer in one context versus another. I mean, a subtext here is that that I think is relevant to neuroscience, that I only briefly alluded to in the presentation, is that, you know, we're often using many models at different stages, and a lot of the models that we're using just to get to the phenomenon that we care about are mechanistic models in one way or another. And so in some contexts, that might be what we really care about, is that model, but and it's using it in an explanatory way. But in other cases, we might use it to provide evidence of some other phenomenon that we're caring about. And so that's kind of the background idea about the fact that we're often using these several models, but it's not like when we use in a measurement role, it doesn't have its explanatory force that it had before.
So would you say the explanatory force is sort of primary somehow? And if it has that explanatory force, you can also use it as a measurement tool? Would you say there's a hierarchical relation there?
I think that's right. I mean, this is actually a part of the presentation and the paper that I want to think more about, because I mean, I'm just saying this because my thoughts here are quite murky still. I think you're right that there's somehow primary in this context.
I mean, I think this is a very interesting discussion to have, and a research topic to continue working on, because they use models all the time and we develop them over time. And usually we start with like, it's the sketch to schema development story somehow. We start with a rough model, and then we get more data, we improve the model, we use the model to explain the phenomena we find, as in the data patterns we see, and then we refine the model all over again. So there seems to be something very interesting to be said about how models function and how they get put to use and how they get developed in science, and how scientific discovery might be driven by models. So I think this is a really interesting topic.
Yeah, so this is so in the, you know, as I'm sure you well know, in the mechanisms literature, it's often sort of mentioned that, you know, as we develop descriptions of mechanisms that causes us to sort of change our characterization or recharacterize the phenomena that we're trying to explain. And I know there's some people that have written papers specifically on that topic. So I kind of see what I'm trying to allude to here is that during that process, there's often sort of two interesting ways in which we're using a model. And part of that process is that we're using, we might use a model in different ways, because that ongoing process of revision is one where a model might, okay, well, this does a pretty good job up until this point, so I'm going to use it in a bunch of other situations, even though it's not like that model is settled science. It's not like we know that's the correct model, so we continue to use it even though it's incomplete, to sort of feed back into not just explaining the same phenomenon, but to change how we explain other phenomena as well.
I'm still not quite sure if calling it measurement versus explanatory role gives the right sense of the dichotomy here, but it's probably a conversation to be continued outside this meeting.
I'll just make one sort of small comment about that. So first of all, I think that you're right, and I went back and forth about what the best way to refer to these things. Part of my inspiration for referring to the measurement role is because in modeling, I'm kind of corrupting maybe a more precise sense that people sometimes talk about, which is that a measurement model is only ever a model that's already achieved some sort of validity in terms of many, many applications. And so signal detection theory, multidimensional scaling, these are going to be your classic examples of sort of measurement models. So I kind of have that sense in the back of my head, but I'm not sure it's right for me to use it, because it might be a misapplication of that notion.
Especially if we're talking neuroscience and computational neuroscience, you might be thinking about brain activation data that's modeled in specific ways. I don't know how much time we have. I haven't actually asked my big picture question, but I also want to give Nico a chance to be a discussant here. So I'll shut up for now, and then we can come back if there's time. Thanks.
We will probably have time for a second round, but thanks for this first round. I guess that was helpful. Nico asked the permission to share some slides, and I granted him his permission. Actually, he's welcome to share his slides. Can you find the share content button? We cannot hear you. Probably your microphone is, the software is still looking for the microphone of your laptop.
Did you press the button at the bottom, because it's showing the mute button? Oh, there we go. Please try to remove the earphones, Nico.
So now?
Yeah.
Yeah, okay. So is there an echo now? Is that a problem?
That seems fixed.
Okay. All right. So I'm excited that we're doing this. So CCN is a struggle, of course, to bring together these different disciplines, and then to define what we mean by explanation and by model and by mechanism. So I'm excited that we're linking this up with a literature and philosophy, which is really helpful for sharpening our conceptualization of how to draw these connections between our theories of computation in the brain and the different kinds of empirical data, like behavioral data and brain data. And there's not many people who can connect these disciplines. So you have a background in both of them, and you're among very few people that are really trying to do this and have experience with the empirical science as well as an understanding of the philosophical literature. So I think that's super important, and I hope that you'll keep exploring this and write more papers about it. So by and large, I agree with the things you've said, and I think it's super useful to better define these concepts. There are maybe some fine points where I'm still sort of struggling to sharpen my own understanding of them, and maybe we can find like some points that where we slightly disagree or where we could have a discussion. So I'm gonna just give sort of a simple kind of what I take away, or what I now, after hearing your talk and having read your paper, I've slightly maybe changed some of my definitions. So I'm just going to share my doodle. See if this works. Can you see this? Should be coming up.
Yeah, I can see the doodle.
So there are these three important terms: explanation, mechanism, and model. Explanation I put at the top because that's what we ultimately want. We want some form of explanation, but that can mean many different things. Mechanism, I think, is a very useful concept, and it helps that there's a philosophical literature on it, which you reviewed in the talk and in the paper, with these different elements of being multi-level, at least two-level, where we decompose the phenomenon into entities and their causal interactions, and therefore sort of go some way toward giving a dynamic, functional understanding of the process that is going on, that produces the phenomenon or underlies the phenomenon. I think the term mechanism is used at different levels. Sometimes it's used at the level of sort of verbal explanation, where you want an intuitive or verbally definable story about what's going on. And sometimes it's used at the level of the models, as you define them as computationally explicit, fully mathematically and algorithmically defined models of what is going on. I think we have to be aware of this flexibility of the term mechanism. It's useful at all of these levels, and it's important to remember which level we're using it at. And the term model itself, as already became clear in the discussion with Lena and John, is a complex and somewhat vague term. So in neuroscience, almost every paper uses models in some shape or form. But when I think of cognitive computational neuroscience and say model there, I mean a very specific kind of model, which I would also describe as a brain computational model or a task performing model, also sometimes described as a process model, and you described it as an information processing model. So to me, all of these are key because they link to the cognitive process. So they need to be models that actually perform the cognitive process that we're trying to understand. And then another question is, can they also additionally be related to the brain? Right, so that relates somewhat to Darden's distinction between the sketch and the schema, where maybe the sketch is sort of thinking toward mechanism, as Lena also suggested, toward mechanistic explanation, but at the sort of verbal level where we're trying to get some intuition, whereas a schema would be potentially at the level or closer to the level of a fully defined mathematical model that does something, that does the information processing, even though it might lack a lot of the details that, of course, are present in the brain. And this should not be seen as some kind of drawback, but we want models to simplify and to abstract. And so the goal is not to have a map of the world that's the size of the world, right? We want something that is simpler, that captures the key elements, right? So this brings me to this distinction between plausibility and fidelity. And after reading your paper and hearing your talk, I now think of it this way. And this is a bit of a simplification of what you said. So some of the distinctions you introduced in your talk, I'm ignoring here because I don't completely understand them. So maybe that's a good point where you could criticize, and because we want to have a bit of a discussion. But let me just, like, for me, it's useful to articulate how, after reading your paper, I now think about it, and then you can tell me where that is off or falls short of insights already had in the philosophical literature. So I think of plausibility and fidelity as related concepts, where fidelity has the stronger requirements, and each of them can be cognitive or biological. So plausibility means that it's possible to imagine something, right? So it's plausible to me that X happened if I can easily imagine that it happened. And this already highlights the key problem with this, which is that it's inherently subjective. What is plausible to me might not be plausible to you. It depends on, what models I have in my head, what mechanisms I might understand. And the fact that I can't imagine something doesn't mean that it's impossible, right? So, this is why the concept of plausibility is deeply problematic. And so I can see why some people might argue that it's even incoherent and that we might want to drop it. However, my intuition is that that is unwise, right? And I cannot 100% justify that. Sometimes in life and in science, we have to make these crazy bets, right? Because either way, we're making a decision. And even if we don't have the perfect solution, we have to make a call, right? And my call for the next 10 years of my research is that this is still a useful concept. This is a concept that matters to me. So plausibility, so biological plausibility in particular, would mean that it's easy to imagine how the algorithm we're proposing might be implemented in the brain with neurons, right? And it's problematic, but it is still a useful concept. And cognitive plausibility would mean that it's easy to imagine the proposed algorithm explaining behavior. So we can, because cognitive science, even though the term is cognitive and it refers to what goes on inside the mind, we can't measure the mind except through behavior. And so cognitive actually refers to being empirically grounded, not in brain measurements, but in behavioral measurements. And then as we go from plausibility to fidelity, we add requirements. So fidelity is more challenging. Fidelity means that it's not only plausible, we can not only imagine this this algorithm or this model explaining the phenomenon, but we have determined that it fits the data in a detailed way. So, for example, you have the cases where reaction times can be predicted from a model, and that would be a detailed pattern of behavior that is predicted by the model, and that would be sort of evidence toward fidelity. And biological fidelity would mean that it fits detailed biological data, right? And now all of this is sort of very high level and very vague, and it will not satisfy John Krakauer. But I think this is where we have to start. And then we have to engage this concept of fidelity, which I think is equally problematic as plausibility, but equally important, right? So we have to consider that in order to determine the plausibility, because it's inherently subjective, we might need simulation of models in order to determine whether the set of mechanisms we're proposing, when implemented and fully specified, can actually produce the cognitive phenomenon, or whether it can actually be implemented with components that the brain also has at its disposal for implementing cognition. And for fidelity, we have this great challenge, which I think is a fundamental theoretical challenge of defining how to measure fidelity, right? It's a very, and it's a very loaded term in this sense. And I think this is a grand challenge for cognitive computational neuroscience to define what would satisfy us. What kinds of detail, at what level of detail, what kind of data do we want to explain? And how do we deal with the fact that when we measure two animals, they're also going to produce different data, right? So we have to negotiate what the criteria should be for fidelity, and that will be the criteria by which we select models. And I mean in an inferential framework, so in a statistical framework where we can say this model is significantly better than this model, or there's a Bayes factor of whatever between these two models, or one model fully explains the data, it reaches the noise ceiling, and there's no variance in the data that is not noise variance that the model cannot explain. So I would relate these two problematic but also important terms to what you called how possible and how actual. So you made the distinction between how plausible and how possible, but I would think of them as closely related. So plausible means we want to be able to imagine how it's even possible with these components to implement the proposed mechanism. And how actual, that's when we actually go to the data. So at the level of plausibility, things fail pre-empirically, right? So we can just use computers to help us imagine, to overcome this problem that sometimes things that are hard to imagine are nevertheless possible. And then before even seeing any data, we can eliminate some of the models, which just can't do the cognitive task. And then we need to go to the second level where the empirical data come in. And that's where what I call fidelity, where we actually compare models to data. And so I feel like, this is what I'm kind of, because I'm stubborn and, I stick to, the way I think about things. So that's what I'm, where I am at the moment. And maybe I'd like to hear your thoughts on where that falls short, or where, some of the additional distinctions that you introduced are absolutely necessary.
So, so I think that listen, what you said is, I think it's very much the same thing as kind of what I had in mind. Just there's sort of terminological differences and choices. So, I think I was, as you're talking, I think that something that I should have been clear about was that and it's unfortunate that I wasn't clear about this in the talk because it's such a crucial point, is that how plausibly models, the presumption is when talk about being more or less showing some sort of correspondence to the mechanisms that you care about, the assumption is that is a result of that could involve things like showing that model captures actual real world data. So it could be driven by background things that we already know about, but it could also be that that's because the model has been shown to be successful for certain kinds of data sets. And so there's a sort of different distinction between, has this been applied to actual world data sets versus actual in the sense that the variables or whatever parameters of the model map onto the properties of the mechanism that explains the phenomenon. So, so I guess what I'm saying is, like, there's actually in the sense of real world data that we actually have, and that's one sense, versus actual in the sense of the real mechanism that produces the data, so that thing. And so the model, one of them is emphasizing sort of the predictive property of models, which is, how well does it actually capture the data that we have, and the other one is emphasizing its sort of the explanatory force in the sense of how well it corresponds. So I don't think that there's actually too much daylight between what, I mean, there's terminological differences, and I'm actually, to be perfectly honest, like I went back and forth whether or not to adopt the terminology that you and Douglas use in terms of fidelity. One thing that you mentioned that I think is very interesting, that is that I think you're right to highlight the epistemic nature of the idea that the models are plausible, right? It's like, we think this is how plausible given what we know so far, but that's a separate thing from what the, in fact, actual correspondence is of the model to the thing that we're trying to explain. And so you're right that plausibility is kind of constrained by what we know, so relative to our perspective. And that's definitely something that I was not emphasizing enough, I think. And I think part of what's interesting about that is that I had this analogy that I made between about the idea of gradient of plausibility, and what I think your point about the sort of epistemic nature of plausibility highlights is that there's uncertainty about where we think we are. Like in the sort of explanation case, we might think, oh, I'm on some sort of trajectory, I'm getting closer to what the right model is to have to explain this thing, but that the epistemic nature of plausibility sort of highlights the fact that we can actually, there's uncertainty about where we actually are in terms of the fidelity of our model versus where we think we are, and that these two things can actually come apart. So I think that that's where I would probably try and apply the fidelity plausibility distinctions, is this distinction between where we think our models are based on our prior knowledge, how good we're doing, versus what the actual correspondence is of our model to whatever the mechanism that we're trying to explain. And that's important because that can also be something that we're trying to do with our models, is in trying to make the phenomenon intelligible, is actually trying to say, make us improve our confidence levels in terms of where we think we are, our model relative to the. Does that make sense, right? So it's like one thing to say, like, is it getting us closer to that where we want to be, or is it giving us a more like precise estimate of where we actually are in terms of our modeling?
That sounds as though you contrast plausibility or criticize plausibility as potentially misleading, and maybe that's related to the subjective nature, and would argue that we should care more about fidelity than plausibility, because plausibility is just what we think as opposed to what the data, where the data lead us.
No, I wasn't saying that. What I was just, what I was thinking was that your distinction, the way you're drawing the distinction between plausibility and fidelity, made me realize that there might be like another aspect of this which I was not appreciating, which was not thinking enough about the epistemic nature of plausibility, and that when I made the analogy to trying to of there being varying levels of model plausibility, when I made the analogy to something like gradient descent or parameter search space or something like that, is that what I didn't capture when I described that analogy, or when I was thinking about this before, is the fact that there can be uncertainty about where we are relative to where we're trying to get to. So we think, and that's reflected that in, a model has plausibility relative to what we already know, but we make assumptions about, how accurate the things we already think we know are, that we're not fundamentally misguided. We think that we're sort of moving with the better models, we're moving in the right sort of direction. But the epistemic part of how plausibility models suggest that, you could sort of analogize that as being like uncertainty. There's always a sort of confidence interval about where we actually are relative to where we think we are, and that's what we can capture with the notion of fidelity. Fidelity is where we reflects how close our model really is to where we want to be, and plausibility is just as it were our sort of sample estimate of where we are, relative to what we think we. That was the way that I'm, at least in the moment, I'm sort of thinking about the distinction between plausibility and fidelity. It wasn't as an argument to say that we should get rid of the notion of plausibility, but rather a way of changing the way I was characterizing it.
But you would say that so fidelity is what we are trying to estimate, but with uncertainty when we talk about plausibility. So that's a bit of a, that's a different conception, right? Because ideally we'd like to have no uncertainty, and then we just have some measure of fidelity, and that would still be problematic because we have to justify why we measure fidelity the way we do. But at least we have something that is more solidly grounded in the empirical data.
But I assume that, but I would think that that the two properties sort of converge, right? That as we have higher fidelity, our models are like also that our uncertainty gets smaller as we get closer to ground truth. So it's I can't hear you. Your mute's on.
Okay. Can you hear?
Yeah.
The way I think about it is that fidelity is a higher bar than plausibility, and it's where we bring in an explicit definition for how to measure the fit, and a statistical framework for doing inference using this measure, and the empirical data. And plausibility is sort of a first filter, where we also compare it to things we know about the world. So in this sense, plausibility and fidelity are on a continuum. It should not be conceptualized as a dichotomy, but a continuum, because the plausibility means that the algorithm is consistent with some very general knowledge about the brain, which might be textbook knowledge, which might be from previous studies. So it's not entirely non-empirical, but it is just not sort of empirical in the present study, right? It's not that, it fits very detailed patterns of data, but it fits sort of the big picture.
Yeah. I see what you're saying. Yeah. No, yeah. This is something I need to think about more. I mean, I think some of what you're describing, I was trying to capture with the tripartite distinction between how possible, how actual, and how plausibly. But I think that you're right that about the importance of that. About there's something, as it were, plausibility of plans are pre-hoc to sort of based on what we already know, versus fidelity is sort of now more direct to really, well, how much does this actually capture, say, the data sets that we care about or something like that. Yeah, that's something that I think you're right.
So I'd like to hear Lena's big picture question.
Me too. Okay.
No? I think we both tried to switch my mic on.
Yeah, sorry.
All right. So I think my big picture question ties in with a lot of the previous discussion, both with some of what Nico said, but also what John said beforehand, and also with some of the clarificatory points I raised. So basically, what I tried to come up with is a list of all of the distinctions, Brendan, that you list in the paper. And there were like, I think 7 or 8. There were Mars levels, and you have obviously 3 of them. Then there are mechanistic levels, which are a completely different story. They have nothing to do with Mars levels. Then there is the sketch versus schema distinction that was very prominent in what we just heard from Nico. And also the biological versus psychological or cognitive plausibility, well, or maybe even fidelity. I don't know. I don't know about that. But I mean, at least there's this psychological or biological distinction in your paper and also in your talk. There is the how plausibly to how actually trajectory, which Craver and Darden also call what was it, black boxing to gray boxing to glass boxing. And I think that goes along the sketch schema trajectory somewhere, and possibly that's somehow linked to the measurement and explanatory role, but I'm not so sure. Then what about all the other stuff? So we have different kinds of levels. They seem to be, I don't know, one sort of one bin. Then there are the sketch schema, sort of the if you want to say that discovery trajectory issues, that's one bin. And then you seem to be throwing 3 of the other ones that are left into one bin, namely the biology versus psychology, implementation versus computation, and constitution and causation. And actually, I didn't even mention the constitution and causation distinction above. So that's another one you make. And you call it productive and underlying mechanisms, but essentially it's like, at least if you follow Craver and Darden, that's like the same distinction. So let's buy that. And I read you and heard you to be saying that biologically plausible models are models that cite constitutive relations or describe constitutive relations. And we seek, well, if we seek a mechanistic model / explanation, like depending on how you put it, then you're seeking a story about the implementation. So then that would link sort of a scientific domain to a moral level, to a kind of explanation. But I think these are different things. And the same then happens with psychology. Analogously, you say psychologically plausible models describe causal stories, and yeah, they are at a computational or algorithmic Morian level. But again, so first of all, I take your yes to be the confirmation that that's what is going on. So
well, so so what's the big question?
The question is, what's the, like, first of all, is that really the kind of relation you have in mind between these like three distinctions, the latter three I talked about? And then secondly, how does that relate to the other two bins, as I called it, like to the whole level discussion? And how does that that then relate to the whole discovery trajectory discussion? I mean, just using arbitrary labels for now.
So one quick answer is just based on something that you touched on is I would so there's I'm a bit so I make the distinction between the psychological and biological aspects of the multi-level mechanistic explanation. I'm reluctant to sort of take a stand about how I think that relates to sort of like disciplinary distinctions. So I mean,
you don't want to relate to disciplinary distinctions.
Yeah, so I mean, I'm referring to those as the psychological and biological aspects, because trying to capture what I took to be kind of different properties of the explanations that are highlighted, and I'm using those terms because there's I mean, as I said, I say this because I'm a bit agnostic of what I think about this, because if somebody says to me, oh, well, you know, a psychologist, part of it is because I don't like the idea of mapping disciplines to Mars levels. And then
me neither. I would say this is a whole different level story.
Yeah, and I don't necessarily like the idea of mapping disciplines in any sort of strong way to even levels of organization for a mechanism. So, I mean,
good. Levels of organization and levels of mechanisms are still two different things, right?
Yeah. So I mean, something that I alluded to in the paper is that I'm treating levels of the relevant levels of organization for the explanation just being the mechanistic levels.
Okay, let's just take that for granted.
Yeah.
I mean, not every mechanist would agree.
No, I know. In terms of how all the sort of those different bins fit together, I mean, like that's sort of an ongoing endeavor. So I mean, part of the reason, I mean, so you correctly pointed out that I make like a ridiculous number of distinctions that I import from like the mechanistic literature.
That wasn't the point. The point was not it's a ridiculous number. The point was there are a bunch of different things, and it's worth thinking about how they relate.
yeah, and so I think that so some of them, like, I'm not sure of what I think. So for instance, you highlighted like the kind of like search space and stuff, kind of what like you and I were talking about. And I was talking about that, as it were, sort of like in the abstract, and also kind of in isolation from a bunch of the other stuff, for instance, being said about like levels. And so, but there's sort of questions there, like, I mean, if you think that the different kinds of models that people are trying to relate at maybe different Mari levels or whatever are mutually constraining somehow, then, you know, one thing is like, well, how does that constrain the sort of a way that we go from how possibly models? I mean, this is like in fact, like an interesting source of tension sometimes, depending on what kind of methodological approach people take, right? As people say, no, but we know the brain stuff shows us this. It's like, yeah, but we know that our psychological shows you this. So there's actual kind of like, in this, to relate this back to what I was saying to Nico, right? I mean, part of that uncertainty about like where we are in sort of the spaces connected to what level, like which ways our models at different levels are and are not constraining of each other. And that's definitely like, there's a connection there that I definitely don't talk about in the paper. And part of that is just because it seems to me that that's a very difficult and complex sort of story. But I would say just off the cuff, like one of the things that I think it does relate to is that those difficulties about connecting models at different levels, I think is actually one of the things that manifests our uncertainty about how close we are to explaining IP mechanisms. And so that would be sort of interesting. Something I want to think about more is about, that connection between our models, how sketchy they are, and how plausibly modeled we think we have, or how much of like how possibly model. I mean, there's a whole other aspect there is that, our psychological model might be merely a how possibly model, and our other model that we're trying to relate might be a how plausibly model. And so there might be sort of different kind of search spaces that we should be thinking about depending on whether or not we're focusing on the causal or the constitutive aspects. And I mean, sure. I'm drawing deeply from the back of my head, right? But in some sense, one might conceive of these as being the sorts of problems when, I think you talk about this in a paper of yours about like Carl's idea of like a mosaic. These might be issues about sort of creating your sort of integrated explanatory mosaic.
I think that the thing you mentioned about the mutual constraining of these different relations, or the different distinctions, or how you classify a model along these different distinctions might be mutually constraining for a classification and another distinction. I think that's a very interesting thing to go into more deeply. Obviously not for today.
Yeah.
But that's really where there's a lot of work to be done, like figuring out how all of these different relations relate.
Yeah.
Because if we figure that out, I think there's a lot to be said about what's a powerful or a good or a useful model in what context.
I agree. Marco, were you trying to get our attention?
Let's work on this together.
Oh,